Yeah, thank you very much. Actually, I'm very honored to be here. UPenn has a great CS department. The Grass Lab is superb. Here, I'm going to introduce the emergence of a new field. It's called the 3D deep learning. So first, I'm going to overview a lot of the topics and techniques in this new field, and then I'm going to project what should be happening in the future. Okay, so first of all, why 3D? Why we're interested in 3D? So we live in a three-dimensional world. The food we eat, to the clothes we wear, and from the cars we ride to the house we live, they are all 3D geometry. And without understanding to 3D, you cannot say that you'll be able to achieve the big goal, for example, the artificial intelligence. 3D data has very broad applications. For example, in robotics, the robot perceives the environment through its 3D sensors. Like in augmented reality, you will overlay the 3D models on top of your glass. And in autonomous driving, the cars has to understand the world, recognize the pedestrians, the moving vehicles through the 3D point cloud. And in medical image processing, you're also seeing more and more 3D data, like the CT data, the fMRI data. So all in all, you have so many important 3D understanding problems. And I like to argue that the 3D understanding itself is the key towards enabling interactions. So as for our humans, we build artificial intelligence with the mind that we'll build autonomous agent to navigate in the environment, to change the environment, which involves the interaction. You have to know 3D. Let me give you a very simple example. So there's a robot that's equipped with a sensor, and it sees the environment as a 3D point cloud. Now it wants to accomplish a very simple task, to move a chair out of some office. So what needs to be inferred? The robot has to think. So where's the chair? Okay, I have to know the shape. And now it wants to take it out of the office and has to think, where shall I grasp? Okay, and how much force shall I use? Is it heavy or light? And weight, this is a swivel chair. If I drag it, it might rotate and might break other things. So understand the mobility is also important. You see that you have to infer a lot of information from the 3D, right? And you have to know these 3D properties to allow the interactions. So from the AI perspective, our 3D understanding has to involve a number of components. The first is the sensory, that you get to see the 3D world. And then the cognition part, that you are able to infer many properties of objects which are related with the geometry and the physics. And based upon that, you could interact with the environment and make changes that transform the world. Okay, so next I'd like to argue 3D is important. And what is the new machine learning for 3D or deep learning on 3D bring us? So I would argue that we are achieving the 3D perception, and which requires the knowledge of the 3D world. So what does the traditional 3D vision do? Well, 3D vision has been a long topic, long-standing topic. And I would argue that most of the traditional 3D vision focused on the so-called multi-view geometry. So you may have some 3D object, and you have pictures from different viewpoints. And usually the goal is, I'm asking you to reconstruct the 3D out of the many images. So if you have multiple views of a single object, you have the constraints, right? And you're able to reconstruct the object according to physical laws. However, in the 3D deep learning or machine learning era, we have a different philosophy. So let's see. You see this picture. It's actually just a chalk drawing in the street. When you see it, you can't worry. You can't but worry for the child, right? It seems like there's abysmal. It's dangerous. Even though it's just a 2D drawing, you infer 3D. And in fact, this is very common. Like when you see these dot patterns, you see this kind of interesting illusion figures. Even though they are just 2D images, your brain always hallucinates what the 3D structure should be. And why? That is because your brain has certain knowledge of the 3D structure of the world. So you have the geometry of 3D priors. So in the learning for 3D tasks, you try to enforce or impose these 3D priors on top of your sensory data to hallucinate the structures. Okay? And the knowledge comes from some training. And the idea is you would show the machines many 3D structures, and hopefully you have an intelligent mechanism to build a prior knowledge of the 3D world. So that's the motivation behind the 3D learning. So you want to get the priors and use it to guide the understanding. But concretely, what are the 3D learning tasks? I would argue that there are two basic type of tasks. One is the 3D analysis. That is, you're presented by the 3D data. Like say, it could be some volumetric data, could be some point cloud from sensors, or some computer graphics data. I'd like you to infer some properties, like what the object class is, that's a classification task, and what are the parts of a 3D, or what are the objects in the scene, that's a segmentation. Or you may have a number of 3D objects, and what are their relationships? You want to build correspondences. These are the analysis tasks. But also there are a family of synthesis tasks. That is, you want to generate some 3D in some form. Perhaps you're given a single image. I'd like you to generate the 3D point cloud or some other 3D form. Or maybe you have some 3D sensory data which is incomplete due to self-occlusion or occlusion from other objects. But I'd like to know the full form of it. Like when you see a teapot, you have to imagine where the handle is so that you can grasp. Or it could be the modeling-based task. You have some 3D model data, but you want to interpret by some simpler way, like by primitive symbols. Okay, so you see that you are able, well, before these are the tasks of understanding a single 3D or synthesizing 3Ds. But also there are the tasks that tries to link the 3D data with the data in other modalities. And you may link the 3D data with images, you may link it with the text, you may link it with maybe videos. There are many this kind of ways to relate your 3D data with other domains. Because the 3D is the original, the pure form of 3D world, of the environment world, our environment, and the knowledge could live here. Beyond the geometry understanding, there are also the physics understanding. So there are the so-called intuitive physics study. Let's see, you may have these blocks, but from the geometry, plus some simple geometry physical cues, you might be able to imagine, run some simulator in your brain to guess what might happen in the future. So that's called intuitive physics. Okay, so my view is that the 3D understanding is an interdisciplinary study that's relevant to many other fields like machine learning, robotics, vision, cognitive science, which are AI related, or in terms of math, functional analysis, differential geometry, topological analysis, because we're dealing with the geometrical targets. You have to know certain things about that. Okay, so I've given you an overview of why we want to do 3D deep learning, and what is the basic philosophy, and what are major tasks. And next, I'm going to introduce some of the algorithm developed in the past few years, especially with a focus on the point cloud-based approaches. But for the sake of completeness, I'd like to give you a whole picture of it. So the very first question that we want to ask is, technically, if you want to build 3D deep learning algorithms, what is the main technical hurdle? And in fact, in all the deep learning or neural network designs, you have to understand your data well. The statistic of your data determines how you would design the architectures. Like for images, there's a unique representation. The images are often represented as a 2D arrays, and each pixel or each entry is the intensity. Because of this irregular structure, you could adopt convolution on top of it. Whereas in 3D world, in different scenarios, according to the applications, how your 3D data are constructed, there are many possible representations. Let's see. There are the multi-view representations, an image, a 3D object. You get many views of it, which actually gives you the 3D information. The volumetric version, you may have a 3D object. You put it in space and voxelize, decompose the space into regular grids and record, for example, the occupancy. Or you may have the polygonal mesh, which is the most widely used format for 3D data in computer graphics. You represent 3D by a number of triangles. Or point cloud for 3D data, it's just a collection of coordinates, which is the most common sensor output. Or primitive-based models. So a 3D model is made of a number of primitives, and each one has its parameters. So you have the parametric representation of 3Ds. So you have so many different representations. And you have to consider to solve so many tasks. And in terms of research, they're formed a big space, the Cartesian product space, of both the task and representation issues. And the deep learning, 3D deep learning research has been focusing on how would you explore different representation and different tasks. So in terms of the network design, you could think that you want to design networks for the two types, with your 3D at the two different ends of it. If you want to do analysis, you have to consider how to build the networks to take the 3D as input. As for synthesis, how would you generate 3D data? So for images, because of its irregular structure, you could adopt a convolution operator on top of it. But for 3D, applying convolution on top of it is not that easy, or sometimes infeasible. And from what kind of operations can you apply and how these 3D data are formulated, we have a rough categorization. Some 3D representations can be thought as a rasterized form, like multi-view or volumetric. They are basically regular grids. And because of the regular structure, you can still apply convolution on top of it, but you'll face a number of challenges. On the other hand, there are also more geometric forms, polygonal mesh point cloud, or primitive-based models. You will use coordinates or parameters to represent your data. And on this data, you basically cannot directly apply the CNN. And there has to be some clever new way to address the problems. And in terms of representations, you could group the papers or research in the field as these basic categories, like learning on this representation and volumetric representation, like point cloud, mesh, part assembly. So I would say that actually the field develops pretty well, especially for multi-view and volumetric approaches. It's getting more and more mature. But you also see exciting new opportunities for like point cloud or mesh or part assemblies. Okay, so I'm going to introduce each family with, from a high level, starting from the simpler form, that's a rasterized form. So we could apply convolution directly on top of it. And we start from the multi-view representation because it might be most comfortable for you if you're familiar with the CNNs. Basically, we'll consider according to how we design a network for taking some 3D form as input first, and then discuss how to generate output. So for multi-view representation as 3D input, the advantage is that we're able to leverage the huge CNN literature in image analysis. Note that I'm going to cover a lot of things, so to make sure that you get a take-home message before each chapter, I'll have this like one-sentence summary of what you should remember. So multi-view representation, that's pretty simple. You may have some 3D data. You place a number of cameras and take the pictures at different views. Okay, so one 3D model is converted to a number of views. You may record the color information or depth information. And then at every viewpoint, you apply some convolutional neural network independently. And usually, all these networks share the weights. And after you generate some representation for each view, usually you have to do some view pooling operation to aggregate the information together and pass it through a second neural network. given some representation of the whole shape, and do, for example, classification or segmentation. So conceptually, that's pretty straightforward. But the disadvantage is that you have to run many networks, right? And this is usually quite an expensive operation. And you have to decide where to play the cameras. If you have an isolated object, that's simple. But if you're in a scene setting, that's more sophisticated. How do you do the how do you use multi-view representation, the 3D output? And basically, you're attacking the so-called novel view synthesis problem. So you have one view of some object, but you want to imagine what it looks like in a novel view. And humans have this ability, like in psychology, there's the so-called mental rotation experiment or some theories about human 3D perception system. But we want computers to do the same. And behind it, the very basic neural network architecture is this kind of a convolution up convolution structure. So you would take some 2D regular matrix as the input and use some convolution operations, or say the encoder, to create some embedding of the data, and then use some decoder to generate the data as some novel views. That's the output is also matrix. That's a very basic architecture. But actually, there are some interesting ideas explored so far, and I'd like to introduce them. The first is a very straightforward approach. The first work on novel view synthesis using deep learning. So it bluntly follows the architecture. Taking a single image of some object from one view, you use the convolution to generate some shape encoding vector. And also you have a second input, which is a parameter that denotes the novel viewpoint. And you do some fully convolutional operations to get a new vector. Together, you combine them and then decode, get the new view. So that's very easy to understand, I think. Interrupt me if you have questions. And I'd like it to be a little more interactive. What this approach suffers is that usually the output results are pretty fuzzy. Like these are the chairs. If the predicted view is very similar to the input view, you could get a reasonable result. But if novel viewpoint, like this is the input view, this is the novel view, which is very different from the camera view, you see that the result is pretty blurry. That is because you have to produce your shape embedding vector in a very condensed way, right? It's usually a 1,000 dimensional vector. You condense so much, so rich appearance, lighting, and many other informations here. Well, that's not easy. So there's a second idea, that is to consider when you are constructing novel view, you try to copy some information from the observed view. So you try to get some pointer for the novel view. And this is the one my work in, I'm sorry, this should be ICCV 2015. So my work that's using a non-deep learning approach to build these pointers. But you see the basic idea is, suppose I have this chair, I want to hallucinate this novel view. I do it in a patch by patch manner. And for some patch in a novel view, I'd like to know what patches in observed view would be informative to reconstruct it. Right, I was using some information theoretical approach to find relationships. But in a deep learning era, people try to do end-to-end learning to achieve this goal. So that is a paper published by Tinghui Zhou from Berkeley. You have the input view, and you want to generate a novel view. For every point in novel view, you copy some pixel from input view. Essentially, for every pixel in the novel view, there is a certain pointer, right? The pointers could be represented as this flow. So it's a per pixel vector field. Now, the reconstruction becomes, given a simple input view, you still use the convolution up convolution architecture to predict this dense 2D flow field. And then you will use this field to copy pixels and generate the output. And you compare this synthetic output with the ground truth. And interestingly, the whole process is differentiable. You can check the paper to get a sense of why. And you see that using this pointer approach, you get more sharper results. But for the pointer-based approach, you see the obvious drawback. For some of the regions, you could see in both the observed view and the novel view, so no problem, you can copy it. But also there are those occluded regions that really you cannot copy, or it's not suitable to copy. So it's better that you do a certain hallucination. And there is this combined approach. The basic idea is pretty straightforward. Given a single view, you predict those flows for the areas that has low overlap. Okay, you have a partial shape at the novel view, and then you hallucinate using the convolution structure to complete the missing parts. This approach gives you the best results on rigid shapes. See that for these cars, the novel view seems to be pretty clear, sharp. Okay, so that's the approach that you copy and then you complete. But the drawback of the approach is that if you are testing it on some rigid shapes, it generally works well, because for rigid shapes, the geometry variation is limited. Whereas for more sophisticated objects like humans, the deformable shapes, still the previous approach suffers, both in terms, well, mainly in terms of how would you predict the flow. So I have a latest paper accepted by CVPR of this year that attacks the novel view synthesis problem for the deformable shapes. It actually will assist the synthesis process by the depth estimation. So think that you have the input view. If I'm asking you to predict some flow vector at novel view, that's difficult, because you have to take the rotation angle into account. However, if I'm just asking you to predict the depth of every pixel, that's kind of a simpler problem, right? Because you don't need to care about the viewpoint change. And once you get the depth information, you're able to lift the image from 2D to 3D. And this lifting allows you to predict a forward flow from your current view to the novel view. But this forward flow is usually not complete. So we also add a flow completion stage to hallucinate the complete backward flow. And in this way, we could do a better job for this kind of a novel view synthesis problem for deformable shapes. Okay, so I guess for my introduction to the multi-view representation, I will stop here. The next representation is the volumetric one, which is more 3D. So volumetric data is very popular. Like for MRI data, that's volumetric. In structural engineering, people have to use the finite element methods. A lot of times, they also use this kind of volumetric data. For physiology, they also have this volumetric data about the Earth shell. So if you want to do deep learning on volumetric data, in the research-wise, you always have to face the complexity issue, computational complexity. Think that you're doing a 3D convolution, right? For the 2D convolution, the major computational cost is in the lower levels. Like the complexity will be quadratic with respect to your resolution. Whereas for the 3D case, the complexity will be cubic with respect to your resolution. So that prevents you to use very high resolution 3D data. And you usually have to quantize a lot, which loses a lot of details. But we also have this interest.
I always said that this question, why doesn't separability in the convolution help in the 3D?
This convolution.
You do either one in 2D and one in two direction, one in third, or three separate one-dimensional.
Right. Right. I think that's a good question. So first of all, the underlying assumption for convolution is the spatial invariance, right? So think that maybe, well, in 3D space, still you have these corners, you have these 3D lines, right? And you do share some spatial patterns across different locations. So that makes the 3D convolution, I think at least the argument is still you could use it. On the other hand, in the 3D space, we do observe that a lot of spaces are hollow, right? So this kind of, I mean, if you are capturing this kind of spatial repetition using convolutions is quite a waste of computational power, right? And actually, in one of my NIFS paper of 2 years ago, we showed a very obvious, actually kind of an obvious observation. That is, for some 3D data, if you quantize it with finer resolution, the spatial occupancy becomes less and less. So if you represent the shape by 32 by 32, 32 by 32 by 32, then roughly 10% of the voxels are occupied. But at the resolution of 100, well, the occupancy rate decreases to 2%. So in order to capture the 2% occupied cells, you do dense 3D convolution. In a way, it's pretty stupid. So you have to consider how do you reduce the computational complexity, but I agree that there should be a more principled question that there should be better ways to capture the statistics, local statistics. But let's see, argue from a computational complexity perspective, one of the data structure from computer graphics could be helpful. That is the octet-tree structure. So you have some 3D data. First of all, you put it in a very coarse 3D space. And then you will check which of the cells, well, in the conventional 3D volumetric representation, you will equally subdivide all the cells, right, until they are very fine, right? If the resolution is high, you will have many, many cells. But using octet-trees, that's different. You could only care about those areas that has some content in it. Let's say you put an object in a very low spatial resolution grid. Okay, every cell is occupied, and you subdivide it. You find that some of those cells has nothing in it. You further divide, and you find that more and more cells has nothing in it. So you will get rid of these cells. You don't need to compute it. So when you do convolution, you only work at those locations that has content. In terms of programming, yeah, that gives the idea of the octet-tree networks. But in terms of computational, algorithmic issues, the difficulty is in order to conduct convolution, you have to be able to retrieve its neighborhood. If you have the regular grids, that's an easy task. But for this kind of octet-tree type of structure, it exploits the sparsity, and you have to be a little bit smarter. So the best practice seems to be using a hash table to index the neighborhood relationship. Mm-hmm.
A quick question. I mean, the other thing that sort of shows up in all these representations is that what you end up representing typically is actually surface. So,
right.
Particularly if you're dealing with scan data, that's really all you see.
Right.
Comment on what convolutions look like when effectively what you're getting is data in a two-dimensional manifold embedded in a three-dimensional space. So.
Right. Right. Exactly. Exactly. You're essentially working, deal with the surfaces. Yeah. So if you're working on, deal with the 2D surface in 3D, there must be some smart way, right? That makes the computational complexity scales quadratically. Yeah. So what if we want to generate 3D data in the volumetric space? Still, the difficulty is in complexity. A straightforward approach is you have a number of input views. Like for every view, you use some convolutional approach encoder to convert it to some shape embedding and then concat them together. And this time, we want to generate a 3D shape, different from the 2D generation test that use 2D up convolution. You just use 3D up convolution, right? 3D up convolution. You could do this. However, this computational complexity-wise is still quite expensive, like you are generating for every cell. Well, in order to scale it up, you could consider to use octatree. But this time it's more challenging because in the 3D as the input case, your octatree structure, after you get the data, you immediately get it. Now this time, you have to generate some structure. Right? You have to generate from the data, you generate the structure. There's this working on the problem. The basic idea is you try to generate the tree structure in a progressive way. Like you have the tree, you first generate the shallow layers and then gradually go deeper. And like you first generate a low resolution cuboid. But for every cell, before you predict whether it is empty or filled, now you have 3 states: empty, filled, or mixed. If a cell is predicted to be mixed, it means that it's half empty. And you should continue the splitting. So you do this process progressively until you get a high resolution output. However, you also see that the errors might accumulate, that if you do a better job in shallow layers, the errors may propagate to the finer layers. Okay, so that is the deep learning on the rasterized form. And next I'm going to introduce something on the geometric form. Okay, the first is how do we do deep learning on polygonal meshes. And remember that if we want to take the meshes input, essentially we're doing deep learning on graphs. So in NIPS of recent years, Professor Yan LeCun from NYU has been, a number of others have been saying that the graph CNNs are fantastic. But if you check more carefully, you find that the major application scenario for graph CNNs are actually on the 3D data, on the geometries. Okay. So first of all, we have to realize that for the 3D that we're processing in this scenario, they are the surfaces. And you want to do the convolution on the surfaces. And when you do this convolution on the surfaces, you have to consider the geodesic distance on it, like the shortest distance between any 2 points. On the 2D side, if I have a point on the 2D space, you will find its spatial support for the convolution operation, which is usually by L1 or L2 distance. You find all the points that is within a certain neighborhood. On a 3D case, you will find this spatial surface neighborhood according to the geodesic distance. So for all the 3D data, especially, for all the 3D meshes, you could represent it as some graph. Because for meshes, you have the vertices, you have the faces, and you have the edges. And you can build a graph using the vertices as the nodes of the graph and edges as the edge of the graph. So then, doing a convolution on the graph, on the mesh, it's just doing a convolution on meshes is just doing a convolution on graphs. And you can use the graph distance to replace the geodesic distance on the geometries. So how do we do, if we want to extend the convolutional neural networks, we have to consider how do we design the convolution operation. Oh, maybe it runs out of power.
If anybody has a USB-C and charger?
So this thing's disconnected. Okay, this is not connected.
Yeah, I didn't realize that it's actually not powerful enough.
Sorry about that.
Oh, it's my fault. I guess.
It's powered down.
Right, it ran out of power. But it's surprising that it could last for this long.
Maybe you can just talk.
Right, okay. Yes. I guess I'm going to show you that if you want to do the convolution on those meshes, you have to find a spatial neighborhood according on the geometry. But this introduced a number of problems, like the spatial neighborhood on the surface. That's difficult to compute. We know that you have to compute the shortest distances, right? That's an expensive operation. There are also a number of issues that prevents you to work comfortably on a surface to do the convolution. So there are some alternative approach. Because you are working on a convolution, we know the Fourier theorem that says, okay, the convolution in the spatial domain is equivalent to the multiplication in the Fourier domain. So for the graph CNNs, one of the possible ideas is to convert the spatial convolution to the spectral multiplication. But you have to have an extended series of Fourier analysis. So remember, for the Fourier analysis, if you want to prove the Fourier theorem, the key is you have to find the orthogonal basis on the surface. So the sine and the cosine functions are actually the basis functions on the 2D space. But for the geometrical case, you could also find some basis functions. Well, this time you will take the advantage of the Laplacian-Beltrami operator. But somehow that's actually not that important. But you just know that there's this kind of idea that you can leverage some differential geometry approaches to convert the convolution from the spatial domain to the multiplication on the spectral domain on surfaces. Yeah. Thanks a lot. Right. Yes, maybe, yes, okay, gets bright. Okay. Okay. So basically, for this kind of idea, you have to study the graph CNNs. And there's one problem we just described. It's like on every individual shape, you have to define its spectral domain by its Fourier analysis. But if the two shapes, they are not isometric to each other, then their Fourier space are different. So that prevents you to share the convolutional weights across shapes. And you have to do something clever. And there's a framework called the functional map that's able to relate the Fourier domain on different shapes. So we could actually leverage the tool of functional map to do this kind of, okay, I think we are already here. Yes. So we're able to use the functional maps to link the Fourier domains on different shapes. And this kind of linkage could be incorporated in the neural network architecture design. So in this type of architecture, it's like you take some input data, which is the 3D mesh, and you define some signals on this mesh. Let's say you extract some local features. And then usually you should do convolution, but now you translate to the Fourier domain and then do the multiplication. In the Fourier domain, you will have to use some functional map to align it to some canonical space. And in the canonical space, you translate to spatial domain and then do some ReLU. And this is the equivalent architecture as in the convolution and ReLU as before in image space. Okay. So that is how you would use the mesh as input. But next, I'm going to introduce a bit about how do you use the mesh as the output. And the heart is actually a geometry problem. That's a surface parameterization problem. So suppose you want to reconstruct the surface, like say this mesh. If you know how do you parameterize it, like you know how do you flatten the 3D shape on a 2D space, if you know how do you do this, then you could leverage the convolution, up-convolution architectures. Like taking the image as the input, and then you predict the parameterized form of some 3D. And because you have the parameterized form of 3D, you actually already get the 3D shape. But I'd like to actually tell you that this is not that trivial, because for this parameterization, for the process to convert a 3D to 2D, you have to make sure certain consistency. It's like if the input data, two input 3D data, two 3D shapes are similar to each other, you have to guarantee that their parameterization are also similar. Otherwise, the neural network is not able to find the consistent signals. However, there only exists mature algorithm for genus 0 shapes to do this parameterization. If your shape has holes or indefinite number of holes, how to do the parameterization in a consistent way, that is unclear. This is really a research problem. To predict arbitrary mesh, that's quite a research problem. And there's no principled way to do it well now. Okay. So yes, next I'm going to the deep learning on the point cloud representation. We're very interested in point cloud because this is the most popular sensor data. Like for the autonomous cars running in street, most of the time they will install the LiDAR sensor. And the LiDAR sensor returns to point cloud. As for the Connect, that are indoor scanners, right, they give you a depth map. But if you scan the environment for multiple views and fuse them together, you still have some point cloud. So point cloud is a very simple and elementary geometric format. And deep learning on point cloud is essentially deep learning on sets, right? Because the point cloud is just a set of coordinates, and the order does not matter. If you permute the ordering, it still is the same point cloud. Okay. So we want to design some neural network on the point cloud. Let's say the point cloud has n orderless points in memory. Usually you represent the n by d matrix. N is the number of points and d is the dimension. And by design a good network, it really has to be permutation invariant. Means that if you change the layout in memory, right, you change the ordering, the network should give you the same result. So mathematically, a neural network that is invariant to the ordering of the points, it is a symmetric function. Recall in math, suppose there's a function that takes n arguments. If you permute the arguments, the function value remains the same. That's the symmetric functions. You actually see many symmetric functions, like norms, like the max pooling or average pooling. They are all symmetric functions. So we are looking for a method to build symmetric functions by neural networks, right? Our construction is based upon, this is based upon my paper last year. It's based upon such a simple observation. Suppose that you have this n-argument function f. If it can be decomposed as the composition of three functions, the first, the univariable function gamma, and second is a multivariable function g, and third is a univariable function h. If it's a composition of this kind, the three functions, the g is symmetric, and the f will be symmetric. This is not difficult to see, right? Because h processes each individual points in an identical manner, and the g is like aggregating information across different points, and gamma could be thought as a post-processing. So that's quite a straightforward observation. But observation inspires us to build networks. Suppose you have the 4 points. You first build this function h by a small network, process as each point independently and identically. And then the output of h becomes some spatial encoding of the coordinate, some spatial encoding. It essentially tells you where roughly in the space there are some points. And then you have this g function, that's a spatial aggregation function, right? Combine the output of different h together, you generate a signature of the whole point cloud, and you post-process it. And this g has to be a symmetric function. For example, you can use average pooling or max pooling for it. And in practice, we use max pooling. So this basic architecture is called PointNet vanilla. Obviously, it corresponds to some symmetric function. But you may be wondering, like for such a simple architecture, how powerful is it in terms of the approximation ability? It's like in a family of all the symmetric functions, how many of them could be approximated by such a simple architecture? Well, we could prove that for arbitrary continuous point set function or symmetric function, for arbitrarily continuous symmetric function, you could always approximate it arbitrarily by the pointer net. So that's such a simple architecture has very strong approximation ability, but the cost is you have to use many internal neurons. And you see that you are to process a point cloud. Okay, point cloud has the points that only appear in those points that are like in those regions that are occupied by the shape. But you are only processing each point, not anything else. And the processing of each point could be done by a cheap network. So overall, the point net is quite lightweight. Its spatial complexity is a lot better compared with the volumetric or multi-view representation. Note that the y-axis is in a logarithmic scale, and this is like the number of parameters. Like for multi-view representation, you will have 100 million, almost 100 million parameters. That makes it quite expensive in computation. But for point net, that's very cheap. Saves 95% of the GPU memory and making it a convenient architecture for portable devices. And because we have the spatial aggregation operation, that makes the architecture robust to missing data. So if a certain region of the, well, maybe we first see this curve. The baseline is some volumetric CNN. This is a volumetric CNN. If suppose that you have the complete shape and you remove certain proportion of the input data, the points, and you see that the volumetric CNN, the performance decreases very fast. But if you use the point net, you see that even if you have removed 80% of all the points, the performance almost do not drop. That's quite an important property in applications such as autonomous driving because for these kind of sensors, usually your data are incomplete if there are reflective surfaces or dark surfaces. Let me show you some intuitive examples. Here is the part segmentation experiment on point cloud. All the input are incomplete shapes. They are actually pretty difficult. But the point net is able to do quite a reasonable job to segmenting the parts like the seat, the legs, and the backs. Yeah, they are not really cherry-picked results, just some random sample from the experiments. So it's quite robust. But why it's so robust? Through some visualization, we find that actually the point net is able to detect those salient points. It's like this is the input original shape, which is pretty dense. And the point net is able to find a compact subset of it, like those points close to the boundaries or the skeletons. And they are already sufficient to determine the identity or the segmentation boundaries of the shape. For more details, you can check the paper. Last year in NIPS, we have a follow-up version. Well, the point net advantage is that it's quite lightweight, right? It's already quite effective. But we find that when we use it in very large-scale scenes, sometimes it's not that, we suffer from some problems. It's like you use a single aggregation operation, the function G, to compress the whole point cloud. This might be too fast. Whereas, as we know, in human vision systems or in the convolutional neural networks, there are the hierarchical architecture. So you also introduce some hierarchical architecture. You think that this is a point net, a point S. Let me explain a bit. You have this point cloud, and first you partition it into a number of regions. And for every region, it becomes a small point cloud. So you could use point net to extract the local features. Okay? And in this way, you actually produce a smaller data set, but each point has a higher dimensions. The dimensions are the output from the point net. And now you do this kind of a cluster again, and you use the point net to analyze the feature space. So you do this recursively. Okay. and you're able to achieve the ability to capture multi-scale structures. You're able to capture the repetitive patterns in small spatial local neighborhoods. And it has a number of advantages, but at least, well, it increases the performance for a number of benchmarks. Actually, it also becomes even more robust with respect to the data corruptions. So that is a framework for the PointNet and PointNet++ are frameworks for classifications or segmentations for analyzing individual shapes. But what if we want to analyze a big scene? Okay, the practice of CNNs is like first you develop some neural networks like the AlexNet or the VGG network, and then you have some meta algorithm. You have some wrapper to allow it to do detections in some scenes. Usually here you have to have the ability to do object proposal and so on, so forth. We could also wrap the PointNet family of algorithms by some wrappers. So for example, to achieve the ability for object proposal, and in this work, we combine it with the object detectors. Like if you have the RGBD data from the RGB channels, you do the object proposals, but you lift the 2D bounding boxes to the 3D space, and then in 3D, you use the PointNet or PointNet++ to refine the results. So this is the paper accepted by this year's CVPR. It's called the Frustum PointNets. It's very powerful in analyzing scenes. Actually, it is a state-of-the-art approach in the Kitty 3D benchmark. We beat the companies like Apple and NVIDIA by a margin, especially for the smaller objects like the pedestrian or cyclist. We're obviously better than them, I think, with a margin of almost 10%.
What training example did you use here for the pedestrians? Was it from synthetic, from graphics, or from real?
From real, all from real data. From Kitty 3D. Yes. I think actually when we were developing the series of works, first of all, the number of papers are exploring the architecture, the approaches. And we did that on the synthetic data. And somehow we hope that this line of work will make an impact. So we tested on real data. And hopefully the industry will appreciate. Yeah. So let me show you some of the results. And this is a very busy street. And you see that there are many cars. In this task, our approach is not only able to detect where the cars are, but also we're able to predict the bounding box for the complete shapes, like the complete cars. Of course, this needs certain ability of hallucination, but because we're using the learning-based approach, right? Remember what I stated at the very beginning. You're able to learn some prior information from the data. So you're able to guess where the complete shape is. And you see, for this very challenging cases, it's able to predict the bounding box, the complete bounding box, very accurately using less than 20 points. The approach also works well for the indoor environment. Okay, so that's how we process the point cloud as the input. But also we can generate a point cloud. So if we want to generate a point cloud, this is the problem of generating sets. The very basic high-level framework is still supervised learning. Okay, so in this pipeline, we try to do the experiments on synthetic data. Like from the ShapeNet, we render many images of 3D models, but also we have the 3D format of each model and want to train a network to regress the 3D from the input image. So you could consider use point set as a description, but then the network takes the image as input and will have to predict some point cloud or some set. And there's no prior work in the deep learning community. So this result from my CVPR paper last year, that we're able to predict the point cloud of the complete shape from a single image. Of course, this is through extensive training. The high-level architecture is pretty straightforward. It's like a supervised learning. So for every point cloud, as before, we represent it as a 2D matrix. Each row corresponds to a point, and each column corresponds to a dimension. Like if you use 1,000 points to represent some shape, you will have to predict a 1,000 by 3 set. And for the network, you have the ground truth set. You also want to use a network to predict the set. Now you need to define some loss function to compare two sets. So this is the
last layers, is everything fully connected?
actually, in our architecture design, we find that you could use up convolution for it. It will learn some surface parameterization by itself, but there are a lot of details. Yeah. Okay. So I'm just going to introduce with a little bit careful about the loss function. This is to compare two sets. Okay, so you have two sets in a space, geometric sets. You want to compare them. There are a number of approaches in geometry, and one of them is actually the Earth mover's distance, right? You try to find an optimal